So the next thing I want to talk about is, we've talked about how to think about the entire life cycle of a machine learning project. And the next thing I want to talk about is, how do you actually decide which projects to work on? And the main points I want to cover here are how to think about high impact machine learning problems, and then how to think about assessing sort of the cost or the feasibility of machine learning projects. So, diving into this, I think there's sort of a framework that I really like for prioritizing projects in general, which is you just think about, what's the impact of the project, and then you think about what the feasibility of the project is, and you plot those things on a 2x2, and then you want to do projects that are, high feasibility or low cost and high impact, right? So, general way of thinking about picking projects. And so, what does this mean in the context of machine learning? So, I want to talk about a couple of mental models for determining which machine learning projects could be high impact, or identifying projects like that. And two that I'll cover are, where can you take advantage of cheap prediction, and then looking for places where you can automate complicated manual processes. So there's a book called The Economics of AI, and the thesis of this book is that really the core thing that AI changes is that it reduces the cost of prediction, right? So instead of needing a complicated system or an expert to do a prediction, your machine learning system can do that prediction instead. And since prediction is central for decision making, that means that cheap prediction is going to make prediction be everywhere, even in problems where it was too expensive before. And so the implication of this, if you want to apply this framework, is look for places in your business context where cheap prediction will have a big business impact. Another framework that I like is Software 2.0. I think this tweet kind of summarizes it. Gradient descent can write better code than you. I'm sorry. It just can, right? And I think this is not universally true, but in many applications it is. And so the idea here is that there's a traditional software paradigm that Andre calls Software 1.0, which is typically what you think about when you think about software, right? So you write explicit instructions, and those instructions are compiled into machine code and then are run according to the specifications that you set. Machine learning code, which Andre calls Software 2.0, is a slightly different paradigm, right? So the idea here is that instead of specifying rules, humans specify goals, and they implement those goals by building data sets. And then an algorithm sort of searches for the best program to meet those goals. And so data sets are being compiled into programs via optimization. And why does this matter, right? Well, in a lot of cases, it just works better. And it's also more general, right? So you can apply it to a wider range of problems. And since every program in this framework looks like a neural network, in principle, you should be able to achieve some big computational advantages, right? So you should be able to design hardware that works particularly well for these types of programs. And the implication, if you want to apply this framework, is look for sort of complicated rule-based software where we can, instead of programming the rules, we can actually learn them. All right, so the next thing to talk about is assessing the feasibility of machine learning projects. And so I think, there's, in my mind, three main cost drivers of what makes machine learning projects expensive. And so the most important one at the bottom of the pyramid is data availability. And if data is available, then I think the next thing to consider is how high is your accuracy requirement. And then finally, also important, but maybe less important than those other things, is the difficulty of the problem itself. And so how can you go about assessing these different cost drivers? All right, so for problem difficulty, I think we've talked about a couple of these strategies, but you can look for whether there's examples of good published work on similar problems. If the published work is all sort of new in the last year or two, then that means there's probably more risk and probably more technical effort to reproduce those solutions. I think other sort of underrated drivers of problem difficulty is looking at how much compute was actually needed to produce those results. So a lot of times you'll see like a state-of-the-art paper from Google, let's say, and it'll use literally thousands of GPUs, right? And so even though maybe they've solved that problem for themselves, if you're looking at this problem as a startup, you need to think about whether you really have enough compute to be able to solve it yourself. And then finally, a lot of neural networks are these sort of large models with many weights. And if you're deploying in a compute-restricted environment, then you need to think about whether those restrictions will prevent you from using the solutions that are available. In terms of thinking about the accuracy requirement, I think the most important lever here is how costly are wrong predictions, right? So I think if you're in a situation like self-driving cars where a wrong prediction is very bad, then that's going to make the problem much harder because it's often you reach diminishing returns as you try to improve accuracy. And then for data availability, I think the main considerations here are pretty obvious, but I think one thing that people often miss is thinking about how expensive it will be to actually label this data, right? So if you can find a way to automate the labeling of your data, so have users label data for you, then that's going to really help drive the cost of the project down. So I want to zoom in a little bit on accuracy requirement and talk about why that's so important. So I think if you plot sort of the required accuracy of your projects on the x-axis and then look at the project cost on the y-axis, then in general, I think the cost of projects tends to grow super linearly in the accuracy requirement, right? So getting that extra, moving from 99.9 to 99.99% accuracy could mean a 10x increase in cost for the project, if not more. And so that's why I think this is such an important consideration. So next, I want to zoom in a little bit on problem difficulty. And so this is, I think, one of the core challenges in assessing machine learning projects, right, is how difficult is this problem really? So to caveat the answer I'm going to give to you, I think this is like a notoriously difficult problem to answer. So what's still hard in machine learning? This is an article from the New York Times in 1997 that has a quote that says it may be 100 years before a human beats a computer in Go, right? And keep in mind this is right after computers beat humans in chess. But less than 20 years later, you have DeepMind beating Lee Sedol in Go to become the best Go player in the world, right? So these types of predictions about what's hard or what's going to be hard in 5 years, people often get them wrong. One framework here that was proposed by Andrew Ng is that anything that a normal person can do in less than 1 second, we can now automate with AI. So I don't personally recommend using this framework for yourself to assess the difficulty of machine learning problems, but there is some validity to it. I think there are definitely examples of where this is true. So for example, recognizing the content of an image. Humans can do it in less than 1 second. For a lot of sort of problems like this, we can train a machine learning system to do it. Understanding speech, translating speech, grasping objects, these are all sort of relatively feasible machine learning problems. But I think there are some counterexamples too. Actually, anyone have any suggestions of things that you can do in less than 1 second that it would be hard for an AI to do? Sorry? Expressing feelings, yep. Mm-hmm. I think that's hard for AI still. Come on, what else? Yeah.
Accents and speech.
Accents and speech. Interesting. I don't know. That might be a feasible machine learning problem.
Like Jamaicans, like all Trinidad.
Maybe, yeah, okay. Yeah.
Threat assessment. So if I look at a person coming to me at night,
Mm-hmm.
determine very quickly whether or not I should cross or whatever.
Yeah, threat assessment. I like that. I think you're right. That's probably a very difficult AI problem. Yeah.
Understanding humor.
Understanding humor. Yeah, that's always my first example as well. AI is really bad at understanding humor, and I think maybe particularly bad at understanding sarcasm. I think complicated robotic manipulation tasks, like in-hand robotic manipulation, I think this is more obviously a counterexample when I first made this slide. Now that OpenAI has solved the Rubik's Cube with a humanoid hand, maybe it's less clear that this is really a counterexample. Generalizing to new scenarios, right? If you're put somewhere that you've never been before, you can really quickly figure out, what are the rules of this world that I'm in, and how do I do my best here? But AI tends to be really bad at that. So I think a slightly less pithy, but hopefully more nuanced way of looking at what's still hard in machine learning. A few things that are still really hard, just general categories of problems, is really anything other than supervised learning. And so these are showing a lot of promise in the research world. And they tend to work really well now in sort of relatively limited domains where we have tons of data and tons of compute. But I think these technologies are not really yet making the jump to sort of real world applications. But I think this will change over the next 3 or 4 years. What about within supervised learning, right? So what's still hard in supervised learning? Kind of a laundry list here. Answering questions, as Peter mentioned, is still really hard. Summarizing text doesn't work all that well yet. Predicting video, right? So if I've seen 10 seconds of video, what's going to happen in the next few seconds? Still a very hard problem. Building 3D models. So looking at the world and creating a 3D structure from that. Real world speech recognition. So not on like a data set created in a lab, but to have an app on your iPhone that will always transcribe what you say well, even when it's noisy. Resisting adversarial examples. Doing math, actually. So symbolic reasoning. Solving word puzzles. Bongard problems. So what these are they're sort of like visual analogy type problems. And so what I want to do next is kind of try to categorize, what types of problems are these? So what types of problems are hard? So I think one category is places where the output of the model, right? So the thing that it's trying to predict is itself really complex. And so it could be high dimensional or ambiguous. And so things that fall into this category are like 3D reconstruction, video prediction, and dialogue systems. So high dimensional or ambiguous output is still pretty hard. Places where reliability is required. And so this, for example, if you need really high precision or you need robustness. And so I think, failing safely when the model is making predictions out of distribution is still not a solved problem. And robustness to adversarial attacks and high precision tasks, like if you need to really, really accurately estimate the pose of things, these types of problems are still hard. And then anywhere where you need to sort of truly generalize, so not just interpolate, but extrapolate. And I think the main example here is out of distribution data, but then also sort of reasoning, planning, and causality, where people are making a lot of progress, but it's still not a solved problem yet. And so I think a couple examples from the self-driving world, edge cases are still something that's difficult to solve with deep learning because they're rare. And then actually control of self-driving cars. Most self-driving car companies, their stack is they use a lot of deep learning for understanding the world, but they mostly use traditional control for deciding what the car is going to do next, although that's starting to change. And then operating on small amounts of data. Right? Deep learning techniques in general don't tend to do that well on these types of problems. Okay, so to come back to our running example. So why are we focusing on pose estimation? Well, remember the goal of our company is to do grasping. And so we need to do reliable pose estimation in order to do that. But the traditional pipeline that we've been using uses all of these sort of hand-tuned heuristics. And that makes it slow and brittle and possibly a great candidate for what Andre would describe as software 2.0. And then how feasible is this, right? So easy to collect data. Labeling the data could be a challenge, but we might have ways around that. And we do require high accuracy to grasp an object, but cost of failure is low because let's say we're operating in a setting where the only thing that matters is how many objects can we pick up per hour. And so if we drop one, as long as it doesn't break, that's probably okay. And then the problem difficulty itself, well, there are a lot of published results that exist on this, but we need to adapt those results to our robot and our setting. So, feasible but not trivial. Okay, and so just to summarize on prioritizing projects, I think to look for high impact machine learning problems, I think a couple of things that you can do are look for complex parts of your pipeline and places where it's valuable to have sort of really cheap prediction. And then on the cost side, so the cost of machine learning projects is mostly driven by data availability, but how accurate you need your model to be, and especially how costly wrong predictions are, and how technically feasible the problem itself is, also play a big role. Okay, I'll take maybe 2 or 3 minutes of questions, if there are any.
There's actually a lot of questions.
All right.
I think
maybe we can do a few more questions and run a little bit over this morning.
Yeah, we should just plan on going over.
Yeah.
So the question I like is, why is going from 99 to 99.9% accuracy so expensive?
Yeah.
Isn't it just adding more examples?
Yeah. So I think, so like maybe a little mental math that you can do here is, if you're going from 99% accuracy to 99.9% accuracy, right now you're making a mistake on 1 out of 100 things in your training set, right? And so, if that mistake is because those examples are rare in your training set, then if that mistake is because you need to collect more examples that looks like if the way that you're going to fix that is by getting more examples that look like the ones that you're making mistakes on, then those examples are pretty rare, right? Because you're only really making a mistake on 1% of your examples. And so I think sort of a very rough heuristic is that if you want to reduce the error by 90%, then you might guess that you really need to collect 10x more data in order to do that. And since data is the main cost driver of machine learning projects, 10x increase in the amount of data that you need probably will lead to a 10x increase in cost.
So a few questions are about metrics. So one example is, what would be an invalid metric?
Yeah, let's talk about metrics in that section. Yeah.
Okay, so that's still in the future.
Mm-hmm.
Okay. When working with a new project that you haven't seen research on that project before, how would you establish a baseline from human performance?
Yeah, let's talk about baselines when we get to baselines too. Yeah.
How do you estimate cost of a deep learning project in dollars and time?
Yeah, how do you estimate cost of deep learning project in dollars and time? I don't have a good answer for you here. I think it depends on a lot of things, right? It depends on, how close to things that are really for example, you can take some problems very simple classification problems, and maybe one reasonably good researcher can spend a couple of weeks and get a system that works reasonably well. Then there are other problems where maybe you need a team of 10 researchers for a year or two. And so I think you need to figure out in sort of rough cut terms, how many people are you going to need to work on this? And then you need to figure out how much data are we going to need. Those are probably going to be the 2 main drivers of how much the project is going to cost in terms of dollars.
How do you evaluate the cost of a wrong prediction?
Yeah. How do you, so I think this is very domain specific, right? So, and I think you can do this in relatively rough terms as well. A couple of examples is one would be if you're trying to make a recommendation system, you might say that, well, if we make a wrong recommendation for someone, then, if we do it once, then they're probably not going to care. But if we make a wrong prediction for them every single time, then maybe there's some percentage chance that they're going to get annoyed and leave our platform. And so you can kind of put rough estimates of cost around that. But you could also just say, yeah, wrong predictions in a recommender system are not that bad. So we have low cost of wrong predictions. On the flip side, if you have a place where you're trying to fully automate something like self-driving cars, and the result of a failed prediction means that the car would crash or a person would get hurt, then I think you don't even need to put a quantitative estimate around that, right? That's really, really high cost of wrong prediction. And so you can just say, this problem is going to be very, very hard.